Hi, this is Franklin Nolan. Today's date is September 10th, 2012, or 2015. Reading Database Reengineering Focus on Intense Database Reverse Engineering by Abdul Aziz Al-Suka Asayer. That's Abdullah Azizi Al-Kushayer. That's Abdul Aziz Al-Kushayer. Spring 2004. Database engineering focus on intensive database reverse engineering. Thesis can be found at Chico State Library. Thesis QA 76 Alpha 456 2004. And the library catalog card in the back. Oh, there isn't one. There we go. There it is. Okay, the barcode number is 3 space 0200 space 01581 space 9543. This is published November 12th, 2004. It's $50 replacement if you don't return it. That is Al-Kushayer Abdul Aziz. Database reengineering focusing on intensive database reverse engineering. It's been checked out twice. Once March 3rd, returned February 18th, and the September 9th, 2005, returned August 30th, 2005. So if you'd like to check that out, get some more stamps on here. Okay. Database engineering focus on intensive database reengineering, a project presented to the faculty of Cal State University Chico, a partial fulfillment of a requirement for the degree Masters of Science in Computer Science by Abdul Aziz Al-Kushayer, Spring 2004. Database engineering focus on intensive database reverse engineering, a project by Abdullah Aziz Al-Kushayer, Spring 2004. Approved by the Dean of the School of Graduate and International and Sponsored Programs, Robert M. Jackson, PhD, signature here. Approved by Graduate Advisory Committee, Melody J. Stapleton, PhD Chair, her signature there, and Leonard Fisk, PhD. Nice signatures. Publication rights. No portion of this product may be reprinted or reproduced in any manner except to the unusual copyright restrictions without written permission of the author. Publication rights. No portion of this project may be reprinted or reproduced in any manner except to the usual copyright restrictions within the written permission of the author. Well, I guess I'll have to write to him, but I'm still going to read it. Dedication. I dedicate this project to my whole master's degree, to my parents, my proud parents, to my father who lives in me, who I wish could be here to see my accomplishments, to my mother who prays for me all the time. Right on. He's now a PhD, by the way. Got a degree in Florida. And he's been working for the past 15 years at some place, I don't recall, but check him out on LinkedIn. Acknowledgements. I would like to express my gratitude and appreciation to my graduate committee chair, Professor Melanie Stapleton, for her unlimited support, patience, and advice, and my committee member, Professional Len Fisk, for his assistance and advice. It is with great pleasure and acknowledgement to my dear brother, Abraham Hohund Aid, and my sister, my sweet sister, Hunda Mayada and Nazarene, for her encouragement and prayers. Without their patient support and prayers, I could not have completed this degree. Word up. So once again, with the Publication rights. No portion of this project may be reprinted or reproduced in any manner except to the usual copyright restrictions within the written permission of the author. So I already looked him up. I didn't see an email address directly, but I'm going to go ahead and record this, and I'll look him up later. I'll send him a copy of this. So, if so facto, maybe he can just read it himself. Table of contents, publication rights, dedication, acknowledgement, list of table, list of figures, abstract, chapters, 5 chapters, introduction, 2 components, reengineering, purpose of the project, 2, database reengineering, database forward engineering, data reverse engineering, database reverse engineering, DBRE tool, 3, legacy database analysis, part 1, views of database, part 2, transaction behavior, design recovery, 4, legacy database for forward engineering, requirements, refinement, conceptual design, DBMS, alternatives, and sections. 5. That's not from chapter. Okay, so never mind. Also still 4. Local data model design, physical database design, database implementation. 5. Summary and conclusion, references, appendices, and data dictionary. List of table, internship data directory. List of figures, there are 24 total figures. Database reengineering methodology, top-down approach, bottom-up approach, internship data system user groups, internship system context diagram, level 1 system decomposition, first user group view, second user group view, third user group view, legacy data schema, admin user group SSD, student user group SDD, employer user group SSD, conceptual design, logical database design, data model mapping, physical database design, intern database creation, internship table space creation, number 18. Number 19, administrator privileges user creation, administrator schema creation, internship schema structure, student schema structure, administration schema structure, employer schema structure, number 24 and final. Abstract. Database reengineering focus on intensive database reverse engineering, a project by Abdulaziz Al-Kushasser, Masters of Science in Computer Science, California State University, spring 2004. A database plays a significant role in the organization's success and prosperity, and importance of such database is inherent from the data they are holding. In fact, data is considered one of the most crucial assets of the organization. Organizations are turning into database reengineering as strategic economic plans, indeed to improve or upgrade their existing agency database. They have found that make the decision has turned out to be less expensive than replacing them. This project investigates methods and techniques used to reengineer a target database. Although database reengineering is typically a standalone project, it can be seen as a major part of this traditional stream reengineering. The project also explains the different components of database reengineering, including database reverse engineering and database forward engineering. In addition, this project is to re-engineer a legacy database using a highly technical approach that will ensure preservation of valuable data assets. The outcome deliverability from the reverse engineering of the subject database shall be fed to a forward engineering process. Finally, this project focuses on data requirements and transaction analysis during the reverse engineering process to successfully reconstitute a database conceptual design. Chapter 1, Introduction. From a systems Information systems have been evolving over the recent years due to revolutionary changes in global technology. As a result, the enhancement of software systems, development methodologies, and tools has also become inevitably one of the methodologies that plays a critical role in business competition. Is system reengineering. Organizations are turning to a system reengineering (SR) as a strategic economic plan needed to improve or upgrade their existing legacy systems. They have found that making the decision has turned out to be less expensive than replacing them. 1. That's for references. I'll go ahead and read the references now instead of later. That way you can refer to them if you wish. References. There they are. We have 10 references, so they're referring to reference 1 and 2 on the first page of the introduction. Okay, references. 1. A RETA extracting the extended entity relationship model from a legacy. Relationship Database, Information System, Volume 28, Number 6, pp. 597 through 618, September 2003. 2. E. Tchaikovsky, and J. Cross, Reverse Engineering and Design Recovery, A Taxonomy. IEEE Software 7, Number 1, page 13 through 17, January 1990. 3. P.H. Aiken, Reverse Engineering Data, IBM Systems Journal, 001 690, Volume 37, Number 2, 1998. O. P.H. Aiken, Database I just read that. 5. G. and V. Hoffer, Modern System Analysis and Design, 1996. Good year. 6. C. Larman, Applying UML and Patterns, An Introduction to Object-Oriented Analysis and Design, and the Unified Process, 2nd edition, 2002. 7. H. Jens and A. Wallstein, Evaluating Theories for Managing Imperfect Knowledge in Human-Centric Database Reengineering Environments. Internal Journal of Software Engineering and Knowledge Engineering, Volume 12, Number 1, page 77 through 102, page 2000. Year 2002. 8. El Masari and the Fundamentals of Database Systems, 2nd edition, 1994. Number 9, Roger H. Chang, T. M. Barron, and V. C. Story, A Framework for the Design and Evaluation of Relationship Database, Data and Knowledge Engineering, 21, page 57 through 77, year 1997. Number 10, P.S. Lourdes, Pedro D. Jesus, G. Pereira, and F. Brito, Clusters Relationships into Abstracts, ER Schema for Database Reverse Engineering, Science of Computers Programming, page 45, pp. 137 through 153, year 2002. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are your references. So we're on to the point where they're referring to number 1. You can rewind yourself and you can do that. Reengineering is the examination and alteration of a subject to reconstitute it into a form and subsequent implementation of a new form. Reference 2. According to Tchaikovsky, and Cross, a major difference between regarding systems restructuring and reengineering 2, that's reference 2, the restructuring can be performed with no understanding of the system's functionality. However, the knowledge of structural form is required. For instance, changing the structure of the program has a group of if statements into case of statements. Structure does not require deep knowledge of these statements, behavior, nor program's purpose and domains. Although restructuring a system transforms the implementation of a new form, it does not involve changes due to new requirements. Reengineering, on the other hand, does not require a deep understanding and knowledge of the subject system to smooth the requirements. Redefined process reengineering usually involves modification to the systems due to new requirements not yet met by the original. Two components of reengineering. Systems reengineering SR mainly consists of two main components, and each component can be viewed as a large process that can be divided into smaller subprocesses. The first component is reverse engineering process that follows a natural bottom-up approach to reconstitute the conceptual design of a target system. The second component of the forward engineering process that follows a regular top-down system development approach, reverse engineering. It has been said successful systems of reengineering SR critically depends on the reverse engineering of a system. 3P, page 2, reference 3, page 246. Chico and Cross, reference 2, defines the process of reverse engineering as the process of analyzing a subject system to achieve two goals. A. Identify the system's components and the relationships. Bravo. Create representation of the system in another form or a higher level of abstraction. Page 15. Although most of the current research is used as a definition of Tchaikovsky and Cross, reference 2, others like to make it even simpler by defining reverse engineering as discovering the obvious. As the process of discovering how a system works, reference 4, regardless, it still remains a set of relatively different sub-processes, not necessarily defined, combined together to produce a high abstraction for a target system from the system's code or data definitions. In other words, it is the process of reversing the development cycle of a legacy system to gain a certain level of abstraction. Reverse engineering can also be performed by stating from any level or abstraction at any stage of the system's life cycle. Two common sub-areas of reverse engineering, according to Tchaikovsky and Cross, 2, are redocumentation and design recovery. Redocumentation is the process intended to recover existing documentation from a functional system. Poor or no documentation in most cases is a bottleneck for systems maintainers and analysis. Flowcharts, controls, flow diagrams, and clear systems interrelational component descriptions are and main deliverables from this process to clarify the system's underlying detail. Design recovery is the process of investigating the subject system's components in order to answer questions about what it does, how it does, and why it does it. Previous knowledge about the system's behavior, old existence, design documentation, and experience analysis are key tools needed to perform this process. Types of reverse engineering covered by this existing research include system software database and data 1. Complex software systems can be decomposed into smaller slices in order to ease and expedite the reverse engineering process in which each slice can be processed in a system. Forward engineering is the traditional process of moving from high-level systems abstract to lower level. For instance, moving from the requirements to the logical design, or from the design to the physical implementation of a system, it represents the traditional sequence of a system development's lifecycle based on information gained from the reverse engineering process. 3. Reference 3. The system development cycle might flow different systems engineering methodologies. For example, a systems development may flow a structure approach such as waterfall or spiral. With these approaches, the systems development goes through structured steps such as requirements analysis, logical design, physical design, and implementation and maintenance. 5. Reference 5. On the other hand, the object-oriented approach is used primarily to facilitate rapid systems development cycle. In this approach, the development process consists of 4 main processes: inception, elaboration, construction, and transition. Reference 6. Purpose of the project. The aim of the project is to re-engineer a legacy database using a highly technical approach that will ensure the preservation and valuable data assets. The outcome deliverables from the reverse engineering of the subject database shall be fed into a forward engineering process. Moreover, technical documentation throughout the different phases of the project shall provide consistent and adaptable conceptual images for future enhancement. Another goal of this project is to make use of the latest reverse engineering methodologies. The project proposes development of Tchaikovsky and cross re-engineering methodologies. Reference 2. On the scale of a legacy database system, Figure 1 explains the different phases and methodologies which these projects will put into practice. Source adaptation E. Tchaikovsky and J. Cross, Reverse Engineering and Design Recovery, a Taxonomy, IEEE Software 7, number 1, page 13 through 17, January 1990. Database reengineering methodology, figure number 1 here. Reverse engineering shows the current database going to a current diagram. That's flowing over to the current resolution, but the current diagram from the second figure on the top is showing the flow of information to the new design. Third on the right, current requirements pushing down to new requirements, and those are flowing, that new requirement from the third over from the right on the top row, current requirements, which is going into the new requirements flowing into the new design, which is also flowing directly into from the current design, which is the second over from the top to the right to the new design below, both of which are flowing into the new data, the new database, which is showing a reverse schematic is showing a reverse engineering flow. So it's going backwards. So then it's coming back to, so there's the forward engineering in the end. So this is figure 1, database reengineering methodologies. The subject legacy database has only limited documentation to assist in the visualization of the database design. Due to this, it may not correctly reflect the underlying schema. Therefore, the methodology of this project shall be divided into 3 main phases. The first phase is investigation and analysis of legacy database. Intensive analysis and information collection about current systems is needed to provide strong ground floor knowledge, and more we have understanding about the current system, the more effective a reverse engineering process will be. The second phase consists of a reverse engineering process utilizing the information gathered during the first phase. It starts with the legacy database physical schema and applies to the combination of different reverse engineering techniques to produce the schema conceptual model. Reverse engineering tools such as the Case Studio 2 will be used to some degree to expedite the process. Currently, these tools claim a certain level of accuracy. However, the reverse has shown the inability of these tools to fully deliver the correct conceptual model needed to automate the process of reverse engineering. That is reference 7. Detailed discussion about these, about the use case of case, uppercase, will be addressed in the second chapter of this project. Third, the phase of the forward engineering process of a new target database. Oracle is recommended choice for the target database. However, an intensive study regarding this issue shall be addressed in the text of this project. After the new database implementation, security roles and constraints shall be implemented and activated. Good stuff. Okay, chapter 4. How do we get to chapter 4 so quick? Oh, okay, we're in chapter 4. Holy cow. Oh, I see how it is. The page numbers are mixed up. So it says we're on page 34. Oh, they didn't bind this book very well. Oh well. So it goes up to page 6, and then it jumps to chapter 4. So I'll contact Abdulaziz Al-Kushar. I didn't find his email address. I'll have to join Indeed to get that information, I guess. But anyways, I'll let him know that the book needs to be re-rotated and whatnot. So it jumps from page 6 to 34, which is chapter 5. And then page 7 comes after page 49, which is chapter 2. And then the page number goes all the way up to page 33, and then jumps to 50, which is chapter 5. And those are the 3 errors that I see in the placement of these pages. They just accidentally bound it incorrectly, or there's some other situation. But it'll still read straightforward, as long as the conclusion is at the end, which is not. No, it is. It should be fine. Who cares? It'll read fine. Chapter 4. No, let's read chapter 2, since it was designed this way. Okay, chapter 2, database reengineering. Database reengineering follows a similar method described in the previous chapter regarding systems reengineering, but with respect to the difference between a system and a database. Typically based reengineering is divided into 2 separate processes. These processes are database reverse engineering and database forward reengineering, or database forward engineering. The difference between these 2 processes is ambiguous except for the size of the affected target database and its level of complexity. Small databases within the business domain are intended to be easier and faster to re-engineer, especially by experienced database designers. And such schematics can be easily extracted from the target database schema, recovered a new database, and then reconstructed. Thus, these engineering such database leads to a mutual cooperation between these 2 re-engineering processes. Large databases with complex designs, on the other hand, require an exclusive decoupling between these 2 processes. Experienced database design would be required here, but most of the evidence would still have to be collected and target schema. Although database reengineering might be a part of a system reengineering process, a clear transition from legacy database to a new one must be defined. This transaction includes database reverse engineering, forward engineering, and data migration. When a successful completion provides a consistent and stable backbone for the system reengineering. Database forward engineering. The database forward engineering process in the context of database reengineering represents a design process in a database application system lifecycle. We can identify 6 phases of the database forward engineering process. Reference 8. Phase 1, requirement specifications. Old requirements gathered from the reverse engineering process together with the proposed business requirements produce new integrated requirements. The new requirement can be transformed into an improved structure by using requirement specification techniques such as SSD, system sequence diagram, or the old diagram technique, DFDs, data flow diagram. Examples of both techniques are shown in chapters 4 and 3 respectively. Additional documents in the form of text tables or charts is usually provided. Phase 2 conceptual database design. In this phase, the conceptual schema is produced that is independent of any specific physical implementations, and conceptual design involve two parallel tasks: conceptual schema design and transaction design. Phase 2 alpha conceptual schema design. The conceptual schema produced by this phase is a high-level abstract data model form and usually independent of a database system DBMS. Due to this, it cannot be used directly to implement the database. A high-level data model, such as the entity relationship ER model, is required in use of the conceptual schema design. The design of this data model, which is derived from the requirements collection phase 1, follows one of the two approaches. The first is called the centralized schema data approach. Idea behind the approach that is different application transactions and users of requirements gathered in phase 1 emerge into a single large requirement set before starting a schema design. One single schema response the idea behind the approach that a different application transaction and user group requirement gathered in phase 1 are merged into a single large requirement set before starting a schema design. One single schema responds to the requirements set in this design. Once the conceptual schema is designed, internal views for different user groups and applications can be specified by DBA, and assumptions of the approach is that it relies on a central authority, the DBA, who decides how to merge the different requirements and then designs a schema for a central database. If there are many user groups and applications, which implies different requirement sets, using this approach is sufficient because merging such various requirements set is a difficult and time-consuming task. Reference 8. In the second approach, view integration merging the requirements is not done. Instead, a subschema is designed for requirements set. The subschemas are integrated into a global conceptual schema for entire database. The internal individual views can be reconstructed after the integration process. The integration process requires methodologies and automated tools to be used to assist in delivering the integrated views. Reference 8. An example of the first approach is used in Chapter 4 of this project. Conceptual schema design flows an incremental processes approach of different strategies. These strategies include top-down strategy, bottom-up strategy, inside-out strategy, mixed strategy, on top-down strategy. We start with a high-level schema abstract and then apply down refinement and decomposition. Figure 2. Show an example of down strategy. It shows a project entity decomposed into project and meaning, and the meaning relationship split into manage and conduct. Figure 2, top-down approach. Manager, the project, that is manage, and that flows down to manager. Manages the project. Manager also implements conduct of the meeting. Figure 2, top-down approach. Source adapted from the El Masari and Navathi Fundamentals of Database Systems, 2nd edition, 1994. And I'll show Al-Kusha-Sayer any problems with the pages on here, and I'm sure I'll want to have that corrected. If not, that's fine. And then I'll ask him if I can get a copy of his PhD thesis. In the bottom strategy, basic schemas are developed and then built up to these abstracts. Figure 3 An example of the approach, it shows a new relationship being built among students and course entities. So this is a bottom-up approach. There's a student in the course, showing the student, doing assist and take, going to course. That's adapted from the L. Massari and Navathi Fundamentals of Database Systems, 2nd edition, 1994. Okay, in the inside-out strategy, central acts or sets of the abstract are focused on which, then spread out, adding more related abstracts. This strategy is a special case of bottom-up strategy. Finally, in the mixed strategy, combinations of different strategies are used. Phase 2B, transaction design. This phase is concerned with the identifying the applications and transactions that will run on the database. Transactions can be categorized into 3 groups: retrieval transaction, update transaction, and mixed transaction. Reference 8. Transaction behavior gathered through reverse engineering process along the new proposed transaction must be addressed, and in this phase it is important to process the phase parallel with the phase 2 to deliver an accurate conceptual design that reflects correct data models. Phase 3, choice of DBMS. The choice of DBMS is determined by technical and economic factors. Technically, issues like storage structures, numbers of concurrent issue accesses, flexibility and adaptability, maintenance, serves, reports, supports by the DBMS must be taken into account. Economic issues vary from one organization to the other. Phase 4, logical database design. This phase is also called the data model mapping, reference 8. In this phase, we map the conceptual design obtained in phase 2 alpha to a data model that is specific to the DBMS chosen in phase 3. The outcome of this phase, DDL, data definition language, which are statements that specify the conceptual and external schema. Phase 5, physical database design. In this phase, physical storage structures and access path are chosen to achieve the best database performance with different applications. The physical database design is the process of choosing the most appropriate structures for the database files. Indexes the partitions within limitation of pre-choosing DBMS. 3 design guides must be adhered to during this phase: response time, space utilization, and transaction throughput. Phase 6, database implementation. Database can now be implemented using the detailed DDL and SDL storage definition language, and files can be populated with data. Data conversation procedures and migration plans are required to transfer the data from the old legacy database to the new database files. And 6 phases do not have to proceed in sequence most often than not. Feedback from later phases are used to modify earlier phases. Data reverse engineering. Data reverse engineering, DRE, has proven to be a successful approach, aims at reconstructing underlying fuzzy organizational data, reference 3. This managed data can then be used for the reverse engineering process. A data model is the final product of the data reverse engineering process. Serving models then can be integrated to produce one of the large models for entire systems. This model is essentially key in the understanding of data systems, interrelationships, and dependencies. According to Akin, reference 4, modeling is also used in several other aspects, such as, I'm going to read these bullet points: filtering out unrelated details, document Requirements: assisting in the discovery of some business rules, speeding up the re-engineering process, production of institutional knowledge, assisting in the possible organization restructuring, assisting in the estimate of the degree and range of proposed system changes, providing both design and implementation activities, picturing clear organizational data used to support strategic decision making. Some research has proposed different models to represent DRE techniques, DRE. One of the recent, DRE is the data reverse engineering. One of the recent fields of focus of the data model, reference 3, is proposed an interesting model called DRE activity model that consists of 13 activities. These activities are concerned with the data analysis, metadata collection strategies, and output matrix. A model of such structures phase would provide great assistance in reaching a certain data reengineering goal, and activities can be summarized as Activity 1, Systems Identifications. In this activity, the target systems must be identified in terms of input and output data, i.e. what kind of data is going into the system and how it looks and when it emerges. It is important to focus on the data that usually degrades systems performance. Activity 2, cooperation and corrections. Cross-functional nature of DRE, that is the data reverse engineering, DRE, required personal cooperation to perform and access to the system core data. Coordination from the management is also required to share knowledge about different organizational needs. Activity 3, evidence corrections. This activity collects as much evidence as possible about the target systems. Evidence can be obtained from the key specialist knowledge about the target system from old documentation, or from the target system data dictionary. 4, analyze team selection. Activities involve forming an analysis team and defining different levels of responsibility. Team goals should be clear and unambiguous to all members. Activity 5, preliminary system survey. The preliminary system survey is a roadmap that defines the scope and helps estimate the different analysis activities. Activity 6, analysis planning. In this activity, a detailed analysis plan should be delivered, and the plan should consider time frame over systems functional complexity and resource availability. Activity 7, analysis kickoff. This activity represents a transition from planning to implementation and starts the target system analysis. 8, the target system analysis. The target system analysis and modeling are repeated until the analysis has achieved certain goals. This activity is a hallmark of DRE, which is the data reverse engineering analysis, and example of the legacy database analysis as described in Chapter 3. Analysis, Activity 9, data packaging, data engineering to validate, document, and packaging the data assets as desirable format. For example, if the data needs to be delivered to another, the data must be packaged according to the input information of the data system. Activity 10, data integration, the data produced during DRE, this is the data reverse engineering, can be integrated with the other organizational data assets. The integration develop unique organizations to the database systems. Activity data transfer, transportable information of the data is the main output of the activities. A data asset might be exported to different tool formats as needed. Activity 12, analysis measures review. After completing the analysis and data is then gathered, summarized, and measured with predefined matrix. Implementations refinement, and records. Implementation, records, and collections are considered the most important task during analysis. A structured technique presented in 3, DRE, data reverse engineering, has 3 components. 1, functional decomposition. The goal here is to analyze and describe the systems according to the groups of related functions. It is a basic form of a system decomposition. In this component, the system is described based on the functionalities performed within a single process. The current system is examined in a bottom-up fashion to construct the structure chart as opposed to down-up systems decomposition. In forward engineering, a data model decomposition, data analysis play a crucial role in accomplishment in this task. They model the data related to the functional groups represented in the data model components. An example of the functional group analysis of the data model decomposition is described in Chapter 3, 4, respectively. 3. Target system analysis. The analysis can be done in many different ways to gain a better understanding of a large target system. The goal here is to develop a system modeling using a data entity relationship by business rule through the process of DRE, the data reverse engineering. A data repository must exist. Data assets and knowledge produced during DRE are stored. That repository, data models, metadata gathering, form target system analysis are also supported in repository. Over time, the repository will be used as a decision support system to help provide a better information base that helps in the decision making. Data reverse engineering differs the database reverse engineering. Reference 3. In areas of structure, database has more structure form than data, such as the schema or data dictionary. B. Tools. A database is more restructured form than has an automated tool availability to support database reverse engineering than DRE. 3. Scope. Data within the organization's domain is naturally bordered than within the same database schema, where the database share the same business domain. Due to these facts, database reverse engineering, DBRE, database reverse engineering, more often than not is considered a special case of data reverse engineering. That's DRE. 3, reference 3 and 4. Database reverse engineering. Although the database reverse engineering, DBRE, a relatively new subject, such material has been done in the field in 1, 7, 8, and 9. Most of the research agrees on definition of database reverse engineering as a technique of extracting the restructuring the conceptual model for a legacy database. For a nature of reverse engineering database, reverse engineering process involves certainly in some intermediate strategy due to incomplete knowledge about the database being investigated. Reference 9. Database reverse engineering can be achieved by inverting the last 3 phases from the forward engineering process described earlier. However, it is not as straightforward as the process as it may seem. Number 9, the process starts by reverse engineering the schema of a legacy database to produce the conceptual schema design. An example of the process is shown in Chapter 3. This DBRE activity is usually performed in 2 steps. The first is structural completion, in which involves identifying all structures, constraints in the subject database schema. The second, schema enrichment, which is the classification of these constraints. 9. Another approach is to divide the complex problem of reverse engineering into simpler pieces. Earlier we described that the process of debrief is also produced conceptual schema from the database. Subject database schema and found of this approach is based on the fact that debrief methods follow a traditional bottom-up methodology. Two problems are associated with this approach and are no abstracts view to the schema until the very end of the project. There is no support dividing the initial problem into smaller ones. Reference 10. Most of the research done in the field of database reverse engineering is based on using the legacy database schema and extracting the schema information to come up with a conceptual design corresponding to the schema. One of the most recent studies done in the field is the work presented by Al-Hajj, reference 1. He summarized previous research done in the field, which can be categorized into three main categories. First category of research depends on human interaction in the schema extraction process. These approaches depend on the user to identify information such as relations and key attributes required for the abstract process. Also, it depends on the user in database engineering to resolve conflict on relation names and help to define schema information in order to identify key attributes. The second strategy approach relies on the query language to extract schematic information about the target database. The focus is on analyzing a joint condition on target database to extract the conceptual schema. Third, a category is the examination of data instances of the legacy target database to extract schematic information. Investigating data instances is not an essay process and involves a lot of uncertainty, particularly in a large complex database. The idea of the approach is to define cases, then attempt to discover the relationships between these cases based on the data instances. Debrief tools. The industry has developed automated support in the development and maintenance of the software. These is called computer-aided software engineering case. The earliest commercial maintenance tools date back to 1982, although a few special examples of diagram drawing tools exist earlier. However, case did not become big in the development in 1985. Case is used the computer-based support and software development process. It includes many phases of software project, including managerial, administration, and technical. Case has a great influence on analysis and design, hereby having a huge impact in the reproduction of maintenance costs. Case tools ensure that the 3 C's are achieved: consistency, completeness, and conformance to standards. Reference 5. We can summarize that the potential benefit of case as the following: encourages the interactive environment, reduces maintenance cost, improves software quality, speeds up the development process, allows phase to be repeated, increases productivity. Case tools can be used to support a wide variety of system development lifecycle CDLC activities. A single case product, however, may not have tools to provide comprehensive coverage for all aspects of systems development cycles. This means that the organization may use multiple case products to gain a broad collection of tools. Reference 5. One of these tools is called computer-aided reverse engineering, CARE. And the most of today's cases tools include CARE capabilities. For example, Rational Case Studios and VISO, VISIO, are used that support CARE for certain levels. That's capital CARE, a capital case. Database reverse engineering is a multi-analytical process that cannot be completed using computerization by CARE tools alone. Human involvement is required to accomplish this process. Although most contemporary CARE tools support human-intensive processes, their capabilities are limited to unable to handle imperfect knowledge about the legacy system. Legacy system 7. Misleading relationships and conflicting the undocumented schematics are hard to detect through the use of these tools only. Thus, intensive human interactions during the database reverse engineering process is required. In fact, relying on CARE tools to accomplish this procedure is impossible, but the support is complex process is needed. Chapter 3, Legacy Database Analysis. The internship office at CSU Chico, that's Cal State University Chico, helps thousands of students with career goals and links students and employers to keep data records of both parties in medium-sized databases. This legacy database holds thousands of data records, and security and integrity of the data are very important to the office. Recently, the office has experienced a massive growth in data and has increased the necessity for strategic action to be taken. Due to this, the office decided to switch into a larger and more modern database. In this chapter, the use and combination of UML notation and regular DFD in the legacy database will be analyzed. The analysis will focus on two distinct parts. The first part is the concern with identifying different views of database use in terms of groups, while the second part will analyze different transaction behaviors associated with each user group defined in Part 1. Part 1. Views of the database. 3 groups use the database, legacy database. A layout of the group is described in Figure 4. The first group, Figure 4, internship database system users. It goes at admin view to internship database, to internet, to students, also to employers. Employers view. That is internship database systems users group. Figure 4. The first group represents the students who are the main beneficiaries of the database. The second user group and the administration that represents the office personnel. It is the most important to mention that within the second group there are different views for different personnel. However, we will omit the discussion about these views for 2 reasons. The first is the fact that the internal views within a user group can easily be forced at the interface level instead of complicating user group via schema. The second is that we are analyzing general user group views regardless of internal restriction views that may exist within a group. Third group is the employers or corporations. Employers can have multiple recruiters, as this will be seen in the next section. The recruiters will then post multiple internship positions. These different views are represented by basic web pages. The basic pages are JSP to provide, whatever that means, to provide database connectivity with requirements. Look up JSP. And there's no index. Hopefully you did better on your, I don't mean to insult, but there should be an index. To provide database connectivity with, I can't remember all these acronyms. Everyone wants to do an acronym. Like it's that hard to write the word out. You're explaining to people that are getting this for the first time around. Okay, to provide this, the JSP to provide database connectivity when required. In addition, some of the administration users groups have the ability to access the database directly through the SQL database server and with the pre-designed web page view. Although the web interface developed for these views are friendly and convenient from the user perspective, the fact that the underlying database was designed to match these views caused some database design anomaly. These arguments will be discussed in the design recovery section in this chapter. Part 2, transactional behavior. Transaction behavior is one of the most critical issues that developers use to be aware of. In fact, the different transaction behaviors imply different functions and designs constraints in this section. These functions will be analyzed in the detail, but before this is done, internship database system processes and data files must be viewed, and a detailed analysis according to each different user must be examined. The context system diagram, figure 5, internship system context diagram. The context system diagram, figure 5, the internship system context diagram, shows a system that is one component interacting with a different user group. This extraction of views disregards any physical structure and focuses on the major inputs and outputs of the system. Okay, you have your internship. Announcements go to student. Resume goes back to internship. There's your 0. And from the internship, you have the candidates list that's going to employers. From the employer to internship position, back to internship system. And then you have administration on the bottom portion here. It's cycling in from students' information to internship system. Likely that both from the administration company's information that goes into the internship system that is actually getting to the internship system rather than resulting in a 0. Internship system reports back to the administration. So there's the cycle there, figure 5. Just follow the numbers like dancing. Okay, it shows that the student information enters the system via one of the administrative user groups and cannot be changed by a student. A more detailed discussion on the observation will be presented later in this chapter. The decomposition of context abstract diagram and shown in figure 6. Figure 6 here, level 1 system decomposition. It's a more elaborate design, but it's just more of the same. Just follow the cycles. Follow your nose. Okay, student SSN to student authentication goes to the login info up to 1, our student data file, and then that cycles back into student authentication. So it goes to the student, the SSS goes into here as a function, comes out 1, login information 1, student data file goes back for confirmation back to the student authentication. Following the line down, I'll follow the numbers because there's 2, 3, 4, 5, 6, 4. Here's a subcomponent of 4. 3. Here's a subcomponent of 3. Employer authentication. Employer. Let me see the cycle. There's 7. Final. Student 2. You have the admin authentication 2. So it's function 1, function 2, subfunction 3, 4, function 5, function 6, function 7, subfunction 4, 5, and 6. So all components. So there's 6 main functions, and there's subcomponents to those. There's actually 7, but then there's 6 main functions. So 2 goes from admin authentication login info, 3 admin data files. We got confirmation back into admin authentication, so let's double check. Admin login data, and then 4 we have going from 1 student authentication to student info, student view, internship info going to students list, cycling to employer view, student view, resume, student data file, 5, employer view going to employer info going to employer, which is coming from employer authentication, data, login data, cycling in, You have admin view, go into contacts information to contacts, and 6 internship, which cycles back into 4 into student view. Okay, so file 4, resume, student 1, data, student data file. Okay, so 4 then cycles into 6, internship info. Okay, 4 cycles into 7, excuse me. Internship info to 7, students list, cycles back into 6, employer view. So then we have 3 down here, it goes from employer, login data, employer authentication to login data, back to for the employer. So 3, see the cycles. Figure 6, level 1 system decomposition. This diagram shows general functions of the current system. It is important to emphasize that the goal of the representation of this function of current system, regardless of the actual physical implications, since it has more data files, about 69, than those shown in the diagram. Only the most critical data files have been chosen to simplify the concept and clarify the functions, which is the goal. Criticism of these physical files and their implications will be discussed in detail in the subsequent schema design recovery section. The core processes are highlighted and the above diagrams, and following discussions will focus on those core processes and will omit the behaviors of their ordinary process, such as login, authentications. No, I said it right all the time. Each one of these core processes represents a user group view described earlier. The student's view is the first user group that is represented by process 4, figure 7. I'm going to pause here since we are we're not halfway, but we're about a little over a third way through. Today is September 7th, September 10th, 2015, page 25. This is Database Engineering Focused on Intensive Database Reverse Engineering, Spring 2004, by Abdul Aziz Al-Qasirsi of the California State University System in California, Chico. Thesis QA Alpha 456, year 2004. Once again, the library reference barcode number is 3-0200-01581-9543. Thesis. It's been checked out twice. You want to check it out? You check it out. Have a good night.